Very well, we're going to begin talking about logic, how to connect logical statements, and more. We are on chapter 2, 2.1, logical form and logical equivalence. Very well, so let's by starting a statement or proposition for this chapter. Definition: a statement or proposition is just a sentence that is true or it is false, but not both at the same time. For example, 2 plus 2 is 4. This is one statement, one proposition. Statement 1. Another statement, 2 plus 2 is 5. Second statement, statement or proposition 2. One of them is true, the other one is false. We don't care if it's false or if it's true. We just say that as long as you can assign true or falsity to the statement, that is called a proposition or statement. Obviously, the first statement is true and the second statement is false. 2 statements. Now I expect you to ask, okay, I have 2 statements, I have 3 statements, I have more statements. How can I form a new statement? So your goal is to form a new statement. As you can form a new number by adding, subtracting, multiplying, dividing numbers, you can combine statements and form a new statement. We have different operators connecting 2 or more statements together. First of all, you can always form the negation of your original statement and get a new statement. Negation of statements. You can use 2 or more statements, connect them together by wedge operator. The meaning of wedge operator is and. Upside down wedge operator is another operator that is or. Let us start by talking about the negation of a statement. Suppose P is a statement, not P is the opposite of statement P. And we say not P is the negation of P. Sometimes you see this symbol representing the negation, the same meaning, negation of P. Very well. Next, using conjunction and. Suppose you have 2 statements, P and Q. P and Q is a new statement that we call the conjunction of P and Q. Second statement, that's how we form a new statement. But if we use or, P or Q is a new statement that we call disjunction of P and Q. So far we learned about negation of a statement, negation of P. Then we learned about conjunction of P and Q, wedge operator, and finally, or operator, P or Q, disjunction of P, Q. Different methods, different ways of connecting 2 statements and form a new complex or compound statement. Perfect. Very well. Let us move on to the next page. So when you form a new statement, a new compound statement, your goal is to see when that statement is false, when that statement is true. In this case, we use a nice compact form that we call truth table to analyze the truth or falsity of a new statement. Any statement can be either true or false. So let us form the truth table for negation of P. Truth table for negation of statement P. Any statement like P is either true or it is false. If your statement is true, its opposite is going to be false. If your statement is false, its opposite is going to be true. When it comes to just negation, the truth table is very easy to form. P is true, not P is false. P is false, not P is true. As simple as that. What if we have a more complicated statement, like conjunction or and between two statements? How do we form the truth table? How do we analyze the truth or falsity of the compound statement? Very well. Your statement P can be true. Your statement Q can be true. Very well. What if my first statement is true? The second statement, of course, can be false. So far you have two combinations for PQ. You get two more combinations for P and Q, because if P is false, then you can consider Q to be true. And if P is false, Q can be false as well. So what do? We define conjunction of PQ, P and Q, to be true if both of them are true. If one of them is false, the outcome is false. When it comes to and, if both of the statements are true, the outcome statement is true. If one of them is false, the outcome statement is false. What about disjunction? How do we define truth table for disjunction or disjunction P or Q? Again, we have four combinations between P and Q. True, true. True, false. False, true. False, false. The way that we define disjunction is saying that the outcome is always true. It's false if and only if both of the statements are false. So true, true gives you true. True, false, true. False, true, true. False, false is going to be false. Very well. Okay. Let's take a look at this example. Our goal is to construct the truth table for this compound statement. So let us break down this statement into smaller pieces and then form the truth table. P or Q, then you have P and Q. Then you have the negation of P and Q. And finally, you connect these two statements together. So P or Q, P and Q, negation of P and Q, and finally the statement itself. Very well. When it comes to a truth table, you must have P, Q, original statements written on the left-hand side. If you open different discrete math books, you see they always start by saying that, okay, the combination for P can be true, true, false, false. Then for Q, you can say that it's switch between true, false, true, false, true, false. Then the first compound statement is P or Q. It forms your next column. Then you have P and Q as the column after P or Q. Note that negation is attached to P and Q. So you get your third compound statement. And finally, your last statement is P or Q and not P and Q. Okay, step by step, we form truth table for each of these compound statements. True or true, true. True or false, true. False or true, true. False or false, false. So P or Q, take a look at P or Q table. Let's get back P or Q table, disjunction. That's how we define truth table for disjunction or operator. Next one, P and Q. True and true is true. True and false is false. False and true, false. False and false is false. Okay, so far we formed a truth table for 1, truth table for 2. Now we move on and negate the second column, column 2. The negation of 2, negation of true is false, negation of false is true, negation of false is true, negation of false is true. And finally, you have to connect the first compound statement and the third compound statement. So you can just forget about the middle statement here and just combine this column and this column. What's the connector? The connector is and. True and false, false. True and true, true. True and true, true. False and true, false. So the last column shows the truth table for this compound statement. Guys, any question here? If you have any question, please unmute yourself. You can use chat as well. Let us continue. Next example. Very well. Here, instead of having 2 statements, we have 3 statements. One of them is P, the other one is Q, the other one is R. How many combinations do we get? Last time we had just P and Q. P and Q, 2 statements, 2 squared, you get 4 combinations. Now you have P, Q, and R, 3 statements. So in total you get 2 to the third or 8 combinations. Okay, perfect. First of all, you have to list all the original statements here, original statements, P, Q, R. So for P, it can be true, Q can be true, R can be true. P can be true, Q can be true, R can be false. P can be true, Q can be false, R can be true. P can be true, Q can be false, R can be false. Okay, what if my P is false now? P can be false, Q can be true, R can be true, P can be false, Q can be true, R can be false, P can be false, Q can be false, R can be true, and last row, P can be false, Q can be false, R can be false. Very well. Okay. So first of all, you have P and Q. This is the first compound statement. Then the negation of R, the second compound statement. And finally, you combine 1 and 2, your last compound statement. Very well. For P and Q, you just work with the first two columns. True, 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 false, 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 true, false, 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 true, false, false, true, false, 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 false. Remember that the connector is and. Next column, so this is 1. Next column is not R. You just find the negation of R. R is true, negation is false. R is false, negation is true. True, false, false, true, true, false, false, true, true, false, false, true. And finally, you just work with these two columns. The combination of these two columns using connector OR. Very well. True or false is true. True or true, true. False or false is always false. False or true is true. False or false, false. False or true, true. False or false, false. False or true, true. The last column shows being truth or being false of this compound statement. Let us move on. Okay, let us define equivalence between two statements. We say that two statements, A and B, are equivalent to each other, or we say A if and only if B. We write A if and only if B. We can also write A double arrows B. Informally, A is the same as B if and only if they have the exact same truth values. Then you say that these two statements are equivalent to each other. Like X is equal to Y is the same as Y equals to X. Of course, these two statements are equivalent to each other. Let's go over some examples to feel more comfortable about the topic. Example, construct the truth table for these two statements, P and Q, Q and P. So what if we switch the order? Okay, P and Q. First of all, we list the original statements, P, Q. How many combinations? Two statements, 4 combinations. True, 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 false, false, true, false, false. Okay, P and Q. The connector is and. It is true if and only if these two statements are true. True, true, true. True, false, false. False, true, false, 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 always false. Now I want to form this new statement, Q and P. So true, true, of course true. False and true, of course false. True and false, it is false. False and false is false. Do you have the exact truth values? Of course, as you can see, they are the same, and it means that P and Q is the same as Q and P. So you're allowed to switch the order. Sometimes you can use 3 lines to represent being equivalent to each other. Another example, double negation property. Show that not P is the same as P. We call this property double negation property. Okay? My goal is to show that the truth values for not P is the same as truth values for P. It's easier to start by writing P on the left-hand side. P has only 2 possibilities, being true, being false. If P is true, not P is false. If P is false, not P is true. Not P is true, not P is false. As you can see, the first and the last columns are the same, true, true, false, false. So you just proved this property. Excellent. So let's take a look at another example. Let's see how do we use truth tables to show that 2 statements are not logically equivalent to each other. Okay, for example, not P and Q, and not P and not Q. We have 2 compound statements. Our goal is to check to see if their truth values are the same or not. As usual, we write down the original statements, P, Q, true, 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 false, false, true, false, false. Not P is the negation of P. So you get false, false, true, true. Then not Q is the negation of Q. False, true, false, true. Then we form the inside compound statement, P and Q. Then we negate it. P and Q. Okay, true, true, true. True and false, false. False and true, false. False and false, false. The negation of true, false, false, true, false, true, false, true. So this is the truth table for not P and Q. What about not P and not Q? The combination of not P and not Q. False and false, false, false and true, false, true and false, false, true and true, true. Okay? Here you have 2 columns. Let us compare these columns. Here you have false and false. They are the same. True is different from false. True is different from false. And true is the same as true. Since 2 of these values are different from each other, it means that not P and Q is not the same as not P and not Q. Another example. Very well. Not P and Q, not P, or not Q. What about this case? Very well. Let us list the original statements here. P, Q, their total combinations. Not P, not Q, P and Q, not P and Q, so this guy is here, and not P or not Q. Guys, compare these two examples. In previous example, the connector in between was and. In this example, I changed the connector into or. So, not P and Q, false, true, true, true. Not P or not Q. You're combining these two columns using connector or. False or false, false, false or true, true, true or false, true, true or true, true. As you can see, these two columns are the same. It means that not P and Q is the same as not P or not Q. It means that if you distribute negation over and, you get not P, the negation of and is or, not Q. Not P, negation of and is or and not Q. We call this De Morgan's law. We're going to talk about this. Just for now, note that the negation of and is or. So as you guessed, the negation of or is and. Symbolically, we write not P and Q is the same as, is equivalent to not P or not Q. Okay. So can you conclude that not P or Q is the same as not P and not Q? The answer is yes, and you can prove it using truth table. The above two logical equivalences are known as De Morgan's laws of logic. Very well, let us take a look at the De Morgan's laws and what you learned in algebra. Your goal is to show that if x is not greater than 2, it's the same as saying that x is less than equals to 2. Or if you say that x is not less than equals to 2, it's the same as saying that x is greater than 2. Or the negation of x greater than equals to 2 is the same as saying that x is less than 2. So this is the negation of x greater than 2. The negation x less than equals to 2. And this is the negation x greater than equals to 2. Perfect. So what's the negation of x? Is between -1 and 4 is included. So if you just graph this interval, you get -1, you get 4, and all numbers in between. The negation, or the opposite, is all numbers on the right-hand side of 4 is not included, or on the left-hand side of -1 is included. So mathematically, you can write it this way. All numbers like x greater than 4 is not included, or all numbers less than equals to -1, -1 is included. Some definition of tautology. We say that a statement is a tautology if it's always true. So tautology is a statement which is always true. We usually denote tautology by T. We have something that we call contradiction, which is a statement that is always false. Contradiction is a statement which is always false. We usually denote a contradiction by C. Very well, let's go over some examples. Show that the statement P or not P is a tautology. Then show that P and not P is a contradiction. So by changing the connector, the operator, you're getting two different types of statements. Okay, perfect. P has only two possibilities. It can be true, it can be false. Not P, the negation is false. True, P or not P. True or false is always true. False or true is always true. So as you can see, P or not P is always true and it is a tautology. What about P and not P? True and false is false. False and true is false again. So the outcome is always false. You got a contradiction. So these two statements, compound statements, are examples of a tautology and contradiction. Another example, suppose you have a tautology like T, which is a statement, and you have a contradiction like C. Show that if you form a compound statement, P and tautology, it's always equivalent to P itself. But if you form a compound statement, P and a contradiction, the outcome is a contradiction. So I expect you to ask, can I use this tautology and contradiction that I used in previous example? Yes, you can form P and P or not P. On the left-hand side, you have P and P or not P. Since it is a tautology, you can write T next to it. P and tautology is P. So we use these rules to simplify a compound statement. Wherever you see P and P or not P, you can just quickly write P for P and P or not P. You learned about a contradiction like P and not P. So if you ever see P and not P, you can quickly write it is a contradiction. It is always false. By using a truth table, you can see P and a tautology is the same as P. That's why we can replace these two. These two are equivalent to each other. And P and a contradiction is always false, which is the same as contradiction. Very well, here's a list of important logical equivalences that you need to know. To simplify any compound statement, you can use any laws that's mentioned here. The first law is called commutative law. P and Q is the same as Q and P. P or Q is the same as Q or P. Associative law, P and Q and R is the same as P and Q and R. The same thing for OR operator. P or Q or R is the same as P or Q or R. Next law, distributive law. You can distribute AND over OR. You can also distribute OR over AND. P and Q or R is the same as P and Q or P and R. Again, you can distribute OR over AND, P or Q and R. For distribution, you have P or Q and P or R. Number 4, identity laws. P and tautology is the same as P. P or contradiction is the same as P. Negation laws. P or not P is always a tautology. P and not P is always a contradiction. Number 6, double negation law. Not P is the same as P. Idempotent law. P and P is the same as P. P or P is the same as P. Universal bound law. P or tautology is the same as tautology. P and contradiction is the same as contradiction. De Morgan's law. Not P and Q is the same as not P or not Q. Not P or Q is the same as not P and not Q. Absorption law. P and Q is the same as P. P and P or Q is the same as P. Negation of tautology and contradiction. The negation of tautology, as you guessed, is always a contradiction, and the negation of contradiction is always true, and it is a tautology. Let us move on to conditional statements. Suppose you have two statements. You can form a conditional statement by using an arrow, P, then Q. P implies Q. P is the hypothesis, and Q is the conclusion. How do we form the truth table? First of all, you have 4 combinations of P and Q. P implies Q. True implies true, true. True implies false, false. False implies true, true. False implies false, true. That's how you define a conditional statement. Very well. Example. P then Q equivalent to not P or Q. Guys, please memorize this. This example, which in this case is just a proposition, is very useful. Wherever you see P then Q, you quickly write not P or Q. You cannot negate P then Q directly. It is not the same as not P then not Q. Be careful. The negation of P then Q is not P then not Q. It is false. Very well. We can prove the equivalency between P then Q, not P or Q, using a truth table. Very well. Another proposition for you. Not P then Q is equivalent to P and not Q. How do we prove that? The negation of P then Q is the same as you copy down the negation. Instead of P then Q, you use not P or Q. Then you use De Morgan's laws to distribute the negation over parentheses. Not P is P, not or is and, not Q, not Q. So not P then Q is the same as P and not Q. Definition of contrapositive. Suppose you have a conditional statement, P then Q. So this is your conditional statement. The contrapositive of this conditional statement is not P then not Q. Not Q then not P. Okay. This is contrapositive. Definition, suppose P then Q is a conditional statement. You can define the converse. Converse of the statement is Q then P. The inverse of conditional statement is not P then not Q. So we defined contrapositive, P then Q. Contrapositive of P then Q is not Q then not P. The converse of conditional statement, P then Q, is Q then P. The inverse of conditional statement, P then Q, is not P then not Q. These are new definitions related to a conditional statement. Let us define biconditional statement. Biconditional statement is the same as equivalent statement. So we say that two statements like P and Q are connected together by conditional operator if the truth values for both of them like true and true is true, false and false is false. So when they have the exact same truth value, the outcome is true. If one of them is different from the other one, it's going to be false. So in another word, you can write P is equivalent to Q, P implies Q, Q implies P, if and only if the truth table works like this. Very well. Order of operations for logical operators. Which one comes first? Which one takes the priority? Remember that if you don't see a parenthesis or anything and you have negation, first you have to work with the negation. Then when you see and or, those operators take the priority. And finally, if you have implication or biconditional, those come last. Here's a question. Suppose you have P and Q or R. Which one comes first? Sadly, it's not from left to right. Not from left to right. We must have parentheses or grouping symbols. Otherwise, we cannot form the truth table for this compound statement. It must be either P and Q or R, or it must be P and Q or R. We must have this or this. Otherwise, we cannot work with this combination. Again, it is not from left to right. Very well. And last page. We want to show that P or Q then R is the same as P then R and Q then R. Note that here you don't have to use parentheses because you know that or comes first, then you have implication. You know that first you have to compute P or Q, then you have to move on to conditional operator. And on the right-hand side, since you're separating and an implication, you have to use parentheses. Perfect. To show that these two compound statements are the same, they have to show that their truth values are the same. First of all, you have 1, 2, 3 original statements, 2 to the third, 8 combinations. True, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, false, and false. Very well. Let us work with the statement on the left-hand side. P or Q, P or Q, then R. Okay. P or Q, true, 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 false, true, true, false, true, false, true, true, false, true, true, false, 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 false. P or Q, then R. True, then true, true. True, then false, false. True, then true, true. True, then false, false. True, then true, true. True, then false, false. False, then true, true. False, then false. It is true. Perfect. This is for left-hand side compound statement. Now for the right-hand side compound statement, first we have to form P then R, Q then R, then combine them using AND operator. Perfect. P then R, true then true, true. True then false, false. True then true, true. True then false, false. False then true, true. False then false, true. False then true, true. False then false, true. Now Q then R. True then true, true. True then false, false. False then true, true. False then false, true. True then true, true. True then false, false. False then true, true. False then false, true. Okay, now you have to form compound statement using P then R, Q then R, which is your last statement. True and true, true. False and false, false. True and true, true. False and true, false. True and true, true. True and false, false, true and true, true, true and true, true. If you compare these two last columns, you can see they are exactly the same. So you can conclude that these two compound statements are the same. And our final example showing that P if and only if Q is the same as P then Q and Q then P. We use truth table on the left hand side to the second 4 combinations: true, 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 false, false, true, false, false. Okay, P then Q, P then Q, true then true, true, true then false, false, false then true, true, false then false, true. Q then P, true then true, true, false then true, true, true then false, false, false then false, true. Okay, perfect. We can use these two to form the compound statement on the right hand side. True and true, true. True and false, false. True and false, false. True and true, true. Okay. Now let us use the truth table for P if and only if Q. It's going to be true if both P and Q have the exact same value. True and true, true. True and false, false. False and true, false. False and false, true. So as you can see, these two columns have the exact same true values. So it means that these two compound statements are equivalent to each other. Very well, we're done with this part.